Welcome to our strategic briefing. Today we're diving into one of the biggest shifts happening in vehicle safety, the move to fail operational systems. Let's get right into it.
This one sentence really says it all. It perfectly captures the heart of this entire paradigm shift. For SAE Level 3 and above, the safety net isn't a person anymore. It's the system itself. And that, right there, completely changes the game for how we design and validate our EE architectures.
So here's how we're going to tackle this, using a classic top-down approach. We'll start with the big picture, the paradigm shift. Then we'll drill down into the real technical challenges and the foundational platform you need. After that, we'll look at why validation has to completely change, and we'll wrap up with clear strategic actions you can take on your projects.
Okay, first things first. We have to be super clear about what this shift is. This isn't just an evolution. It's a full-blown revolution in safety thinking. And it's all driven by one thing: taking the human out of the immediate control loop.
This really lays out the difference. Over on the left, you've got fail-safe. That's our comfort zone, right? Standard stuff for ADAS up to level 2. It assumes a human is always ready to jump in. If there's a fault, the system just bows out. But on the right, that's fail operational. This is mandatory for level 3 and up, and it's a totally different world. Here, the machine is the fallback. It has to spot a fault, keep full control, and safely handle the situation. The responsibility is completely shifted to the system.
So that brings us to the real core of the problem. The most common mistake I see engineers make is thinking this is all about hardware redundancy. But the true challenge, where all the complexity is hiding, is in the software.
And here it is, the classic trap. The logic seems so simple, doesn't it? Just stack two systems together and call it a day. But that is a dangerously simple way of looking at it. So why doesn't just adding more hardware get you a truly fail operational system? Well, it's because without an incredibly sophisticated software layer, you've got nothing. No guaranteed synchronization, no reliable, deterministic state switching, and absolutely no defense against a single bug taking down both systems at once. The result? You could have a deadly delay during a handover, or even worse, a complete system failure.
This is how you solve it. Freedom from interference, or FFI. The best way to think about this is like a safety firewall right inside your microcontroller. It uses memory and timing protection to build a wall around your critical functions, like steering. So if some non-critical part of the software crashes, that firewall makes sure it can't bring the whole system down with it.
All right, let's talk about the foundation, the software platform itself. Look, in this age of high-performance computing and software-defined everything, it's really tempting to just ignore the old standards. But for motion control, that would be a huge mistake.
So with the entire industry buzzing about adaptive AUTOSAR for all the cool high-level stuff, why on earth do we still depend on classic AUTOSAR for the really critical parts, the bits that actually control steering and braking?
Well, the answer comes down to these four things. And for by-wire systems, these are absolutely non-negotiable. You need that hard, real-time performance. You need deterministic execution that classic AUTOSAR guarantees. It's mature, it's efficient, and it's been proven time and again for the highest safety levels. When it comes to motion control, this platform is the bedrock.
Now, the sheer complexity of these systems means our old ways of testing just don't cut it anymore. We can't just rely on physical prototypes. We need a complete revolution in how we do validation.
This number pretty much says it all. The next Euro NCAP regulations are expected to have over 1,200 test scenarios. Trying to cover that with physical cars on a test track, it's just impossible. Economically, logistically, you just can't do it. The scale of validation has completely changed. So the answer is a strategy that shifts testing way earlier in the process, what we call shifting left. First, you use software in the loop to run millions of virtual tests in the cloud. Then, you use hardware in the loop to actually inject faults into the real ECU to test your logic. This completely flips the script. Physical testing becomes the final confirmation, not your main tool for finding bugs. Okay, so how do we take all this theory and put it into practice? Let's boil everything we've talked about down into 3 critical actions for your engineering teams.
All right, here we go. Number 1, adopt pre-certified software modules. These are called ASILD-COOCs, and they will dramatically cut down your certification work. Number 2, enforce freedom from interference right from day 1 of your architecture. Don't treat it as an add-on. And number 3, build a powerful hardware-in-the-loop platform designed for virtual fault injection testing. These 3 things will speed up your development and systematically take risk off the table.
And this really brings us to the final big picture question.
In a world where software is in complete control of the vehicle, our job isn't just about preventing failures anymore. It's about designing resilient systems that can manage failure gracefully when it happens. That right there is the future of automotive safety.